Electromagnetics here in Delft University, and I'm very pleased and honored to have Douglas here together with Lindsay to give the distinguished course for the Society of Exploration in Geophysics. Douglas received his Bachelor of Science degree this year, exactly 50 years ago.
No, nobody's counting. He didn't hear that. I was more like 27.
Something like that.
Yeah.
And he is a very long career, completely devoted to electromagnetic methods and forward modeling and inversion. And he is here to share his knowledge with you. And Doug is with the University of British Columbia in Vancouver for 40 years. And he is
20, actually.
20?
No, it's
40. And the director of the Geophysical Inversion Facility that already for almost 30 years. And this year, SEG will award the group, the Geophysical Inversion Facility, and of course that is under the inspiring directorship of Doug, the Distinguished Achievement Award for the substantial contributions to advancing the science of exploration geophysics. So, congratulations. It's really nice. Well, yeah, this is an honor for me to have you here, even though I have to go because of other commitment. And I wish you a great day, and you too.
Okay, thank you.
Yeah, thank you.
Well, thanks, Everett. And thanks everybody for coming out. It's good to be here, and it's sunny. Notice it's people were telling us it just rained in Holland, but I don't believe that at all. It's been nice ever since we got here. So, yeah. So we're having, this is the SEG DISC course on electromagnetics, fundamentals and applications, and yeah, we're traveling around the world and trying to talk to people about electromagnetic geophysics and kind of show them what the potential is and demystify it and yeah, get people to be really involved in it. But before we actually start that, I wouldn't mind finding out who's actually in the audience and sort of what you're doing and yeah, kind of why you're here. So maybe we'll just start at the back.
I'm Yuki. I'm a PhD student here. I mostly work with seismics, but I also worked on electromagnetics. It's my bachelor. I'm very interested to see all the benefits.
And what kind of electromagnetics?
That was controlled source electromagnetics.
I just started a week ago, my PhD here in earthquake imaging.
Steve, I'm a PhD student. I'm on the near surface of physics, mainly dive investigation. And I'm postdoc in geophysics and electrophysics section, and what I'm working on last week is scattering due to fractures. So I'm also interested in working in electromagnetic characterized fractures.
My name is Ferry van der Hoeven. I work for a consultancy firm and I conduct near-surface geophysical surveys, mainly using GPR and magnetics, but nowadays more and more using EM sensors, but it's all very shallow. I have no formal geophysical background, but I'll do my best here.
Yeah, I'm work for a company. We mainly do magnetics, but also GPR, EM61 we have, G, and much more applications. And most of the time we tell processes and also to what method is the best survey.
Okay.
I'm Chris, I'm also a PhD student in Delft. I work on elastic extension of chamber imaging. The last time I dealt with EM was in the AMS course, so now I need to catch up here.
Yeah, I'm also a PhD student here in Switzerland. I work on monitoring changes in the medium, or the scattering changes in the medium.
mainly cycling or acoustic. But again, as you know, I'm interested in seeing how being able to be applied in that area. And then again, the last time I was introduced to last time, contact with him was in the MS course, so we'll leave it.
Okay.
I'm also a PhD in Delft in geophysics, and my focus is on marine seismics and the effects of the sea on your data.
Hi, my name is Oliver Turnhout. I'm a postdoc at Geoenvironmental Engineering, and we're investigating landfills. We just recently installed a lot of electrodes in depth and on the surface to use ERP and IP to investigate characteristics and water. Trying to figure out how to use it to.
Have you used IP measurements for landfills much in fact?
Yeah, there have been some examples which I've been going through. Some resolution. Yeah, because we have now a 3D grid. We want to be proof it, but it's completely my background also, so I'm also here to.
Okay, good.
I am Ranjini. I am also a PhD student at the Geophysics section. My work is focused on finite element methods, actually, for formal modeling in the imaging process. And I'm extremely new to electromagnetics and geophysics, and I'm just trying to learn.
I'm Eric. I'm a master's student at the University. I'm new now. I'm finalizing a project in electromagnetics for geothermal purpose. I conducted a survey in the Netherlands with CCM and MT combined, and now trying to see if we can use it in an area of quite a lot of cultural noise. We combine these two techniques to still visualize reservoir geothermals.
Okay, good.
My name is Chef Meekes. I work at CNO, which is a research institute in the Netherlands, where we have a long tradition, an old tradition of electrical methods and electromagnetic methods, but the last 10 years we didn't do so much. To pick up again. And I like to combine always electrodes with inductive.
Okay, good.
Receivers.
I'm Rita Streich. I am with Shell doing research on electromagnetics, and I have been working quite a bit on land here. Yuri has been helping us on one project doing land CSEM surveys, which I've been leading. Right now, we're focusing more on marine CSEM and anything related to that. Effects of metal in the ground, for example. So I'm happy to see Lindsay is here. And also on integrating EM with other data. And I have been hoping to bring some colleagues with me from Shell. That didn't work out, unfortunately. So I will take the message along and share with my colleagues later on.
Okay, my name is Jaap Mond. I used to work for Shell in research in Rijswijk, mainly related to seismic, and then later on also the non-seismic methods, that means gravity, magnetics, electromagnetics, electrical methods. I mainly concentrated on CSEM. After my retirement, I started giving courses. I had my own company and together with other people. And I could give courses on seismic data acquisition and processing, also basic geophysical data acquisition and processing, non-seismic methods, so gravity, magnetics, and so on, and reservoir characterization. I used to be very busy in that, but since the oil price is somewhat lower, I have a lot of spare time. I made e-learning courses and so on, but even that didn't work at the moment. So I'm still busy. This next week, say, to around to help people there. But it used to be much busier than at the moment.
I'm Gianni. I'm also a PhD on geoengineering section. Actually, I'm in the same office as Andrew. So we are developing a new technique for reducing surf permeability, and we did a lot of pilot project, and we would like to monitor our implementation. So in the previous case, we used ERT to see whether we reduce surf permeability, whether we introduce our compounds into subsurface. it was really nice, but the resolution is not high enough. That's why I come to here to see any possibility for improvement or other technique.
Good. Thank you for that. So that actually is pretty valuable information for me, because we've got there's a lot of stuff that I could talk about, and it's helpful to kind of know what the background of people is here. Basically all academics, I mean, mostly PhDs and postdocs, a lot of background in seismic, not so much perhaps in EM. And yeah, maybe we could fill some of those gaps up and yeah, advance where everything is going. So as I said, this is the DISC 2017 put on by the SEG. I'd like, first of all, to offer my thanks to Rita for helping set this up, especially Ruben, who's been absolutely instrumental in getting us going, and to Everett Slobs. Without these three people, it really is the people in the local, or at the local level where we go to, that make all the difference in the world. So I thank all of you. I thought maybe before we really start, I'll give you just a bit of the background about myself, and also just make a couple of comments with respect to inversion. So I was inspired by a couple of really great people. Bob Parker, you know that name, Freeman Gilbert, George Backus in the late 1960s. And these people were all kind of pioneers in the geophysical inverse problem, and I happened to be at Scripps Institute of Oceanography and working with them. I just want to have this is a timeline here, and I thought it's kind of useful just to sort of see where inversion has progressed and the kinds of problems that we could solve. If you go back to 1975, the kinds of problems that people could work with are basically 1D, maybe DC resistivity and magnetotellurics, something that you only had 50, 75 variables to work with. Came along in about 1985, where you had workstations, and that allowed problems of maybe 1,000 or a couple thousand variables to be done, and that allowed the DC resistivity and the IP problem to be solved. About 1995, computers were getting big enough that we could solve basically our full 3D problem. And maybe this is one of the things that separates out the electromagnetics and the non-seismic group from the seismic group, because in seismology you just always need to have lots of variables and big meshes. But we can solve the full problem in some cases, like gravity magnetics, maybe with 100,000. The trade-off is that you don't have very good resolution, but at least you're solving the exact problem. By the time you get 2005, we can start to solve the 3D frequency domain EM and time domain EM with a few sources. The introduction of two things. One is direct solvers, so that you could take a matrix and factor it. And the second is all the microprocessors, so you could have multi-cores, actually allow much larger problems to be solved. And I think we're here today at the DISC, where we can basically solve the full 3D problems for frequency and time domain EM with actually a lot of sources. There's a number of things that have really advanced the whole field. One is basically instrumentation and data. I mean, we can now acquire both high quality and large amounts of data that we just had not been able to see before. And that allows us to do very large scale problems. Here's something where we have a groundwater problem in California, in various continents, both in North America and in Australia. There's actually continental-wide programs to recover. These are all the magnetotelluric stations that are going to be there, and they're eventually going to invert all these data to get a 3D composition of
Can we ask questions in between?
Sure.
Are these permanent, all these stations?
No, these are moving. So
Oh, I see.
these are different grids acquired. And yeah, so then an offshore, perhaps that resonates with a few people, marine CSEM, and trying to use that for de-risking. And I've got a case history that will talk a bit about some of these problems. The other thing is that we're in a situation where things have changed remarkably with respect to web resources and open source computing and resources. And that allows us to kind of collaborate with people, to share, to make some tests, and just kind of changes the way people work. I will be talking more today. I'll show you examples today, and we'll talk more tomorrow about SIMPEG, which is open source package for forward modeling. But these things all kind of allow a different kind of way of interacting with people and getting things done. And the other thing is we've got many applications that are now arising. So anyway, electromagnetics, for instance, could be used for mineral exploration, contaminants, groundwater, geothermal energies. We talked about that. Unexploded ordnances, hydrocarbons, slope stability, geotechnical. So there's a huge number of problems out there that are important, and perhaps it's possible for electromagnetics to play some role in these. Maybe not be a complete solution, but at least play some role. So that seems that we've got the basic ingredients. We've got, first of all, problems to be solved. That's important. We've got high quality data. We've got the ability to invert these different EM data sets. And we've got web tools to communicate. So, okay, seems like we should be good to go. But the question is, okay, what's the roadblocks? Why isn't this really taking off? And there's actually a lot of roadblocks, and just through a couple of conversations here, I've already kind of identified. And that is first that, in general, geoscientists just don't really realize the role that EM can play. I mean, it's just haven't really kind of connected with it. The terminology is sometimes confusing. Don't really understand the technique, you don't understand the technology, and people in EM talk about, oh, the real part of the data or the imaginary data, like, okay, what is all that stuff? And the other thing is, it's not intuitive. Seismic is wonderful in this sense because you can see a wave go down, it reflects off, it comes back. It's like, okay, I got it. Electromagnetics is not that way. It's a diffusive process, and the data, you cannot look at the data and kind of understand what's going on. So that makes it confusing. The other thing is, roadblock is really coming to grips with, okay, what's the connection with my problem, whatever it is, and resultant physical property that I'm interested in, namely, usually electrical conductivity. And unless you have that kind of connection between your problem and your physical property, it's really hard to make it go away. Even if you kind of get through all of these, then you have to say, okay, well, I'm going to choose a survey. So in seismic, I mean, again, there's different kind of surveys you can use, but they're all basically setting off a gun or some kind of explosive and getting acoustic or elastic energy coming through. In electromagnetics, as we'll see today, there's just a whole host of surveys, and they can be quite different. Should you use a DC survey? Should you use a survey that is working in the frequency domain or time domain? And where are my surveys? Are they in the air? Are they in the ground, on the ground, on the surface, in the borehole? And always the big question, what do I expect for resolution? Resolution is always the big thing here. What scale can I see? And finally, the other thing that isn't existing in a lot of places, and this is sort of a comfort level. You've got a problem, you want to somehow solve this problem and see if EM is useful. One of the things you'd like to do is find somebody else who had the same problem and figure out how they did. And so the question is, are there example similar to mine that which EM has been applied successful. So these things here are really all kind of roadblocks because they don't exist really at this time for most people. So the goal of this course is actually to kind of get rid of those guys. So we're going to spend a day, and by the end of the day, I think you'll feel like there's a big cross through most of this stuff. So that's the goal. If we can accomplish that, I think we're in pretty good shape. So it seems that we're in a position where we've kind of got a perfect storm because we've got all the pieces. We've got problems, we've got high quality data, we've got the ability to invert these data, we've got web tools to communicate. And so maybe the disk is just coming, it's the right thing at the right time to kind of combine all these and take advantage of this perfect storm. It's a good idea, but there's one important ingredient that's missing. Anybody? Pardon me?
Us.
Us. Perfect. Exactly. We need to have, you know, the bright young people, lots of creative ideas actually can make use of this. And we got one sitting over here, Lindsay, if you haven't met her. And another of my co-presenters, depending on where we go, is Sagi Kang. Both of them are completing up their PhDs and ready to go ahead and take advantage of all of this. So the goals for the disk, I'd like to inspire you. I just see the variety of problems in which geophysics or EM has made a difference. And we want to illustrate that effectiveness through case histories. So a large amount, we actually look at places, we'll present the fundamentals, but then see, okay, how did that actually get applied? And when you see the successful application, you're like, oh, well, maybe I could use that. We want to build a foundation. I want to tell you about the basics of electromagnetics, what the basic principles are, and kind of explore the fundamental understanding. We're going to do that through a number of apps that have been developed. So this is software pieces of code that allow you to kind of ask questions and to explore. And we've got open source resources on our website, GeoSci, that it's kind of our portal to a lot of information on, you know, both on the fundamental side as well as on the application. Want to set realistic expectations. This is extremely important. Very often, geophysical techniques, EM, have been oversold. I mean, in principle, they seem like they should work really well, but in practice, you know, the resolution is not what you need or whatever. So you need to have an idea for a particular kind of survey, you know, what you might be able to get out. And another objective, and this is actually a really important one, is to kind of develop more of a community here where people can talk and interact and to share problems, to share data, to share questions, and just continue on towards like an open source environment where, you know, you're acting more as a collective community. And the last thing is kind of related to that is that we want to sort of capture case histories that are, you know, people are working at around the world. So one of the things we're going to ask you later today, and it'll be for tomorrow's topic, is for you to talk about the kinds of problems that you're doing, and we'll just sort of see where all that fits in. So when we talk about open source resources, here's our open source resource. It's GeoSci. If you open it up, here's a front page that looks like this, and there's sort of a whole sort of index of things that you can look at. One of the motivations for doing this is a textbook. I'm not sure. Is there anybody that has seen this textbook published by the SEG, Electromagnetics by Geophysics? So how many people raise your hand?
Yeah, I've seen
yeah. So it's a wonderful book. It's got all kinds of information in it, and it's a classic for graduate students to look at. All my graduate students have worked through it. But you know, it's not a particularly insightful thing in many respects because you can't interact with a lot of the stuff that's in there. So that's been a motivation for us to develop this, you know, the EM GeoSci. And part of that problem is kind of connecting the theory up with the application. So we've got a number of case histories that we're presenting, and we've developed a kind of a format for how a case history might be presented. And I think most geophysicists would kind of work through the thing in the same kind of order, where you first of all ask, okay, what's the question that I want to address here? You know, what's my physical property? What survey should I use? What are my data looking like? What processing should I undertake? What's my interpretation? And then some kind of synthesis to see how well you can advance with the project. So we find by kind of parsing all our work out into these sort of 7 steps, that it really helps in that communication of trying to figure out, okay, where exactly am I in this process, so you can communicate with other people. And it's also a nice way of kind of condensing down the information that you've got for a case. So all of these resources are open source, and you're invited to offer opinions. You can edit things. You can make you know, suggestions. And with that, we will actually have an open source resource that continues to grow and have input from a number of people over time. I mentioned apps, and the question is, okay, why an app? So this is just a piece of software that allows you to ask a particular question. And really, I think it's motivated a little bit by this. So here's an equation out of any EM textbook. It's a couple of Maxwell's equations. And you look at that, and that actually has a huge amount of information in it, but it's not particularly obvious what everything is doing. And so, you know, images and ability to interact is crucial. So the apps will kind of look like this. You probably see a lot of these things. You've got, you know, various fields that you can adjust, and you press a button, computations will be done, and you can make a plot of things, and you can ask questions about, well, what if I did this, or what if I did that? That's a very, very effective way of learning and engaging with the material, and we're going to have a lot of those you know, that are really available on the EM GeoSci, and we'll show some of them today and tomorrow. So how do we achieve all these goals? Well, we're going to try to connect with you know, relevant applications. We're going to have a particular problem, so we're going to select a survey that might be appropriate. We can use the apps to ask some questions and maybe glean some insight, and show the success of everything in case histories. So that's kind of how we're actually going to try to step through that system of roadblocks and get rid of it. So here's our agenda for today, and it's a very ambitious agenda, but I think you'll find it actually really insightful, because we're going to do something which I don't think is generally done. I've certainly not seen it done before, and that is to take a look at basically, you know, Maxwell's equations and step all the way through from the beginning to the end. So we're going to start off with DC resistivity, or people talk about ERT. Then we'll do just some fundamentals of EM, just to kind of refresh, you know, what the basics are. We'll look at inductive sources, both in frequency and time. Then we'll look at grounded sources. So this is the marine CSEM problem. Look at natural sources, so that's magnetotelluric, so there's your geothermal problems in there. Ground penetrating radar, sort of higher resolution, shallower depths, very high frequencies. And then something which is very important, and we've already seen this for the landfills, induced polarization. The thing about being able to see this whole thing right from the beginning to the end is that it puts everything in perspective. You suddenly, by the end of the day, you kind of like, okay, I get it. I've got this kind of a problem. I could use, you know, I could use an inductive source on this, and I could get X amount of information. Or I need actually to have a grounded source and do things. So that's the agenda. And it is a very ambitious agenda. And there's a wide variety of information, but there's also a wide variety of backgrounds of people that are here. So I hope that there's something here for everybody, so that you go home at the end of the day and you say, I'm glad I spent that day. I learned something. I'm kind of good at. This course is not for the experts. So Leah, maybe you're sitting there thinking, well, I know all this stuff. But I go for coffee every Saturday morning with a group of people. We've done this for a lot of years. I think it's like 24 years. Every Saturday morning, we go to the same coffee place, same people have coffee, but they always have a saying. And you walk in, and here's one that was, I thought, particularly appropriate. It's a gal by the name of Doris Lessing. And she says, that's what learning is. You suddenly understand something that you've understood all your life, but in a new way. And I think there's a lot to be said for that. Like, so sometimes you feel like, okay, well, I know all that, but maybe if I can present something just a little bit differently, it becomes richer. So you learn, kind of get a little bit more insight. So I hope that's it. I hope there's something here. The DISC is a 2-day event. Today is formally sponsored by the SEG. Tomorrow, DISC Lab is sponsored by the Geophysical Inversion Facility. Our goal there is, we want to talk to you, capture information about your local problems that you're actually working on, and just discuss where EM could play a role or how that might work. And we'll also use tomorrow to talk about more technical things. It kind of depends upon the audience. We were just in Australia, and there everybody was really interested in EM decoupling because they were working on all kinds of IP problems, and they've got big conductive overburden. Other places they were really interested in CSEM and wanted to have, you know, extra tutorial information and things like that. So there, we can mix or match. We've got lots of material. The most important thing, I think, is to try to make sure that we're talking about things that are really of interest to you and that make a difference. The tour, we used to think 30, but I think it's probably going to be 27 locations. And we're trying to capture problems that people are working on. And you can appreciate that by the time we've done this, and even with this limited group, if we had 10 people that talked about problems that they were working on, these are captured, they're put onto YouTube if you agree to that. And it means that it's there then for perpetuity and for other people to take a look at and say, oh, well, what are people doing in Delft? That's interesting. And, so it's a way of helping that communication. We do have a blog. I'm not sure, has anybody looked at our blog? Oh, a couple. Oh, that's good. So I encourage you to do this. It's a way of kind of seeing what happened in other areas of the world, and it's just a kind of a nice casual way of just finding out how the disk has worked as we've gone around. As we do this, as we're trying to develop and connect, there's multiple ways of doing that. One that's effective both for what we're doing right now and also in future is to use Slack. Has anybody used that or heard of that? Yeah. Yeah, it's good. Anyway, it's just a way of communicating. You can make a group within Slack, and you can share problems, and you can upload pictures, and you can just ask questions. And it's just a nice way of informally doing things. In fact, if you had your computer and you joined a Slack channel here, even while I'm talking, you could write something down, say, this guy's crazy, I'm not sure what he's talking about, but I don't want to raise it with my hand, right? But you can do that. So that's a way of communicating. And then as far as contributing, we're always on the lookout for case histories and content, so people can contribute to our open sources. And SIMPEG, which we'll talk about a lot more tomorrow, forward modeling version using Python. How many people use Python? Oh, good. So it's, I think, it's a way of, yeah, again, communicating through software and exchanging things and trying to, yeah, speed up the whole business of trying to compute things when you've got, especially sets of differential equations or you're trying to solve an inverse problem. So that's kind of what I like to do is just give a really short introduction to EM, just to kind of set the scene in a little bit more formal manner. So I just want to take a look at 3 problems. There's kind of typical problems occur. One is in, say, in minerals exploration. Another is unexploded ordnance. It seems like people in Holland should have a lot of these guys around, but I'm sure it's a problem. People tend not to talk about it very much. And there's water issues. I'm going to talk about these 3 just briefly because they bring into play 3 different physical properties that really are of interest. The one that we're going to concentrate almost entirely on today is electrical resistivity, or its reciprocal conductivity. So the resistivity or conductivity is related to how easy it is for a current to pass through a piece of rock or any kind of metal or whatever. And we've got a table up here. So this is resistivity, it's in ohm meters. And this is very low resistivity, so that means current passes through easily. So here's things like massive sulfides or graphites or salt water. And that's to be contrasted with things that are very resistive, metamorphic rocks, sands, gravel, limestones, permafrost. So up here, notice there's like 6 or 7 orders of magnitude difference there, which is a huge scale. So from seismology, factors of 20% or 40% are really big numbers. Here, we can have many orders of magnitude. A lot of the things that we're interested in are kind of in the middle here, clays, tills, hydrocarbons, The reciprocal of resistivity is conductivity. That's in either Siemens per meter or millisiemens per meter, and it's on this scale. The second physical property in Maxwell's equations is dielectric constant or electrical permittivity. And this is really of importance, especially in ground penetrating radar studies. Permittivity ranges by about 2 orders of magnitude, air being 1 and fresh water being 80, and everything else kind of falls in between. The third property in Maxwell's equations is magnetic permeability. We often just cast it as magnetic susceptibility. Again, that's got a logarithmic variation. There's rocks and minerals that have very low magnetic susceptibility. The big guy on the block is always magnetite. That's very magnetizable. In other words, so if you put a little magnet by a piece of magnetite, you're going to magnetize it. But again, you've got sort of a logarithmic variation. So we've got 3 physical properties that are really of interest. The one that we're going to be primarily concerned with is the electrical conductivity. But any of these systems that we're going to be working with, we'll kind of have this generic slide in which the geophysical experiment is one in which you have a source, right? So you put energy in, it interacts with various physical properties, and you get some data that are So as I said, there's 3 different physical properties, and they're all connected through Maxwell's equations. So we're not going to be very math heavy in this course, but we do need to actually look at Maxwell's equations. And throughout the day, we're going to be flashing this slide up with various things that are whited out or blurred out. But yeah, here's Maxwell's equations in its entirety. These are in the time domain. These are in the frequency domain. And these tell us how a time-varying magnetic field generates an electric field, or how a current generates a magnetic field. So those are the equations. Then we also have to have constitutive relationships. And that will relate any particular field, like an electric field, to a flux. So here's a current, which is a flux, and the relationship involves a physical property. So we got three constitutive relations, each having a different physical property that is involved. And so those relationships plus this actually allows us to solve every electromagnetic problem that we have, so long as we apply a source, and if we have boundary conditions, then this is it. That's all we need to work with. So everything that we do today is going to be kind of based on these equations. We're going to kind of parse them out and look through to see what each of them is really doing, and yeah, show how they can be applied. So, yeah.
It would be helpful, say, if we look at a particular experiment or an app application, that you refer back to the equation again, and that you say, okay, we see in the app now this happening, but look at the equation. You could have predicted that or seen it from the equation itself. So that makes the equations maybe more understandable, giving me a feeling what I'm looking at.
Yeah.
Is that possible?
Well, it is, and I think we can take it one step further, and that is that by showing where the fields are, what kind of fields are available, where the currents are, where the charges are, I think you get a real physical understanding for what the process is. So that combination not only of the equations, but then also of sort of application modules that allow you to kind of show what part of an object is being illuminated by a particular source, that becomes very insightful. So let's kind of parse that down a little bit. So we had our sort of general diagram here. And the first thing we have to worry about is a source. So what are we going to use for sources? So there's 2 kinds of sources. One is inductive source. So this is an inductive source. It's basically a loop of wire that's going to be carrying a current, and that's going to inject energy into the ground. The other is a grounded source. Sometimes it's called a galvanic source. So in this case here, there's 2 current electrodes that are involved. So those are the 2 types of sources, so inductive and grounded. Within any of these sources, I can put a different waveform. I can put in a harmonic waveform. So we usually talk about that as being like a frequency domain system. Or I can put in a transient where I have maybe a time when the current is on and then I'm going to turn the current off. Then there's also a question about location. Where is the source? Well, it could be in the air, and we'll show you a number of airborne surveys. It could be on the ground, or it could be in a borehole. So those are options. That's already a lot of options for sources. And what about data? Well, what could we measure? We can measure fields, right? So we can measure an electric field. So that would involve putting in 2 probes with a voltmeter in between. Or we could measure a magnetic field. So those are the 2 things that we can have. So we can have a choice of fields, electric or magnetic. We're going to distinguish between frequency and time just by uppercase and lowercase letters. So our fields in the time domain will look like this. And then there's a question with respect to which frequencies should I use? is like a really low period or a high period, that would be at a frequency domain. Or if I'm measuring a time domain system, what time channels do I want to look at? So those are options, and each survey you're going to have to kind of make a decision about. Okay, what am I going to do? And then when you have these fields, and there's even a question about which components should I have? Do I want to measure just an X component or a Y component? Do I want all three? And then where are those receivers? Are they also in the air? Could be attached to a helicopter, or they could be on the surface or in a borehole. So again, a lot of options here. So if we come back to these three problems, the reason that I kind of brought them up was that in each of these three problems, although they're kind of connected with a number of physical problems, electrical conductivity is the one that kind of goes through all of them. So because electrical conductivity is so pervasive as far as being a diagnostic property, we're actually going to concentrate on that. So that's going to be the next up. We're going to start to look at something called the DC resistivity. Let's see. So how many people have been involved with a DC resistivity survey? Certainly you guys have done, so ERT. Oh, so actually quite a few. And in what regard? What were you looking for?
Well, we did some landfill exploration, but also quite some bit for archaeology. So we did some department a few months ago.
Oh yeah.
And there's some archaeological dig site there. With the university in order to detect walls on the surface.
Oh, good, good. What was it successful? Or?
Actually, we got some nice results.
Sorry?
We got some nice results back in. We also put it over a certain object that there was very strong evidence that was there. Dome shaped object, which showed quite nicely in the section.
Oh, good. Well, maybe you can talk about that tomorrow. And you've been using it for waste dumps, right? And what other applications?
Salt water, saline water, fresh water.
Ah, yeah.
Clay, sands.
Yeah, good.
Groundwater related.
Yeah.
We had to check for drink water facility of when the clay layer was continuing or was a leak holding it.
Ah. Excellent. Okay. So we've got quite a bit of background in DC. Yes.
And civil engineering, UXO surveys, and archaeology as well.
In UXO?
In UXO, yes.
Oh.
We mainly in Holland, well, the rest of the world as well. We mainly use magnetics, of course.
Yeah.
But in some cases, it's not possible to use magnetics, and then we use, for instance, the GPR or other EM.
Okay. Oh, interesting. Yeah. Very often, some kind of inductive source EM is used for unexploded ordnances. Okay, so I'm going to talk to you about DC resistivity. So the basic experiment here is this. So we've got a source, and we're going to put energy in, and I'm going to try to stick with resistivity. So we're going to use rho, and the relationship between sigma and rho is that one is just the reciprocal of the other. But I will confess I'm probably going to just use resistivity and conductivity intermittently. It's just, you just get used to it. It might be sort of one of the things EM people do. So what's our motivation? There's a number of things. One is mineral exploration. Works. In mines, the biggest problem is water. So trying to use DC resistivity. We have some potash mines in Canada that's been very useful for. Oil and gas, groundwater, talked about saline water just a while ago, and geotechnical issues. So these are just some of the areas in which DC resistivity could be used. So we come back to this table. We showed this table a bit ago. Conductivity varies by many orders of magnitude. The thing that's actually very important, I think, here is that the conductivity is really depends on a lot of things that are associated with the rock. It depends on the rock type, but also depends on the porosity. And then it's how these pores are connected, and then what the nature of the fluid is in the pores, and if there's any kind of a solid matrix in the background. So even if you take what you consider to be kind of the same rock, it could actually have quite a different conductivity. And here's, you can see even in this small sample here, this is just a penny. And you can see how the texture of that rock is changing. So things are not necessarily simple. What I want to do in this is basically just outline what the DC resistivity experiment is. I'm going to talk about sort of the fundamentals of how the experiment is carried out. And we're going to talk about the data and how it's plotted, some pseudo sections. And I've got a case history to show you. It's mineral exploration. And we also have one for dam monitoring using self-potentials and DC resistivity. And we'll see how far we get in that. But we'll certainly do at least one case history yet today. So here's the basic experiment. This is a conceptualized diagram of a mineral deposit in which there's an overburden here that is fairly, has a low resistivity. The deposit itself is looking like this. There's a conductive core. This blue region on top is a resistor. It's called a Gaussian. So that's the thing that you'd really like to find. Actually, it's this mineralization. So you're going to set up this resistivity experiment, which involves, first of all, a source. So we need a current source. So we're going to take a generator and 2 probes and have some currents that are going to flow through. And then we're going to measure some potentials up here. So when we put current into the ground, that current gets distorted depending upon the electrical conductivity of the substructure. And so maybe the current lines look like that. One of the fundamental things that we'll talk about in depth is that as the currents go through the object here, it's going to require that there be electrical charges that are set up. So those electrical charges give rise through Coulomb's law to electric voltages that you're going to measure up at the surface. So that's basically the idea. Put current into the ground flow, or currents go through objects. You're going to end up setting up a whole bunch of charges, and then you record the potentials at the surface or down. So, okay, so that's the basic experiment. How do we actually go from that to, how do we get the resistivity of the ground? So here's our Maxwell's equations again, and here they are in kind of the full glory. But when we're doing this experiment with DC, it's called DC, it's direct current. It's steady state. So nothing changes in time. And because nothing changes in time, there's no, that means that curl of E is equal to 0, or that E could be written as a gradient of potential. And in the steady state, we're allowed to then condense Maxwell's equations. You put it all together, and you actually get a very simple equation which relates the voltage that you have to a current that you're going to put out here. So we're going to stick a current into the ground at some location R, and then the final equation is just a div sigma graph potential that it relates the electrical conductivity and the voltage. Now, in a simple case, when the Earth is just a homogeneous half space, then there's actually an analytic solution to this, and we could write the relationship between the conductivity and B like this, or if we use resistivity, we've got that the voltage is related to the resistivity current divided by R. So why is that important? So imagine that we take a current probe and we just inject a current into the ground. And now you can imagine how the currents are going to flow. Everything's homogeneous, so the currents are just going to flow out like that. And the voltage that we have away from that from that current is governed by this equation here, where R is just the distance between where you are and the current. And so the voltage is going to drop off like that. But we can use this to our advantage in that if we were at any place out here, away from that current electrode, we just measure the voltage, 6.9, and we put it into this formula. So we just simply rearrange this so that we could write rho being related to the voltage is measured, the current, and we know this. So we know everything, and we do that, and we actually get that the resistivity of the Earth is, in this case, 500 ohm meters, which is what it was. Okay, so that's the connection. Measure a single voltage, and we could actually get the resistivity of the Earth. In practice, of course, we can't do that, because to put current in, we actually need 2 electrodes. So we're going to be consistent in that the positive electrode is going, we'll just label it A, and B is going to be the negative electrode. And so if we have 2 currents, we got a positive current and a negative current, then our voltage, or electric potential, looks like this here. And again, to measure something, we actually need to put 2 probes into the ground, connect them to the voltmeter, and we would have voltages at, let's say, for these locations here, and we're going to use the subscripts M and N to denote where the voltage probes are. So, but because everything is linear, we had that previous example where just a current in a half space, we just use the geometry, and so we could actually write that the voltage difference that we measure between these 2 points here is just given by rho times I with this kind of geometric factor, which we then can go ahead and rewrite in these. So the bottom line is that if we have like an A and a B electrode, currents are going to go like this. We measure some potential difference between here. We could actually get out what the resistivity of the Earth is like. So what happens if we start to make things a little bit more complicated? So now, if we put on a layer that has a low resistivity at the surface, then what do you think is going to happen to the currents? So you see the currents in here are just, they're kind of doing what you expected. Here's the positive, here's the negative. If I put in a low resistivity layer at the surface, how is that going to distort the currents?
Most of it is going through the upper layer.
Yeah, so we'd expect, so it's going to take an easy path. So in fact, that's exactly what happens. So the currents, instead of so much down here, there's a lot of currents that are just going through here. And that, of course, is going to distort that potential curve that we have. So now we're going to measure a potential difference, and we plug that into the formula, and we get out not 500, which was the resistivity here, and not 100 ohm meters, which was the resistivity of that, but we get out something in between. We call this number here that is we evaluate through that formula the apparent resistivity. And you can see in here, there is no true resistivity because you've got two units here, low resistivity and a high. So there's an app. I'm not going to demonstrate that right now because it takes a little bit too long, but we'll show you some of these. But there's an app that you can use that actually allows you to change the parameters of that model to see where the currents are and what the potentials are that you would measure, and then you can use that to kind of see. Looking at the currents is a really, really good idea. It just helps kind of figure out where everything is being excited. So there's a couple of things that come into play here. One is called a sounding, and the other is called profiling. So we're going to look first of all at sounding. And the idea with sounding is that, so I'm standing here, and I'd kind of like to see what's happening down below, and especially if I imagine that the Earth is just layered, and now I want to somehow get some information about what's happening near surface and at far surface. So the idea of the sounding is that we're going to have to start off with a particular geometry, and there's a couple of words that are used. One's called a Wenner sounding, where the current electrodes are like this, and the potential electrodes are inside, and these are all kind of uniform in space A. Or you can have something different called a Schlumberger sounding. None of these really are fundamentally different, just slightly different ways in which people collect data. It's good to know the names. And our idea with the sounding curve is we're gradually going to try to build up something that looks progressively, starts off shallow and looks progressively deeper. So here's the first one. So now we'll start. So let's assume that we've got our current electrodes are really close together. You can see what happens here. So this is still the same figure that we had before, where this is the low, that's 100 ohm meters over 5. And now if the currents are really close together, you can see like, okay, well, they're basically kind of going from A to B. And they're more or less in that 100 ohm meter layer. And if we looked at the apparent resistivity, it'd be 100 ohm meters. Okay, so basically you're sensitive to what's happening really close to you. If you make those farther apart so that they're now at this location, now you're getting currents that are going deeper in, and the value of the apparent resistivity is 135. So it's more than 100, so you're starting to see this upper layer. And we can plot this curve out here. So this is basically something that's telling you about the length of your array, and here's your apparent resistivity. You can see as the length of the array gets bigger, we're starting to get an increase in that apparent resistivity. And if we go out even more, now we've got 239, so here's what that sounding curve is starting to look like. So it's all kind of intuitive. You can see that as these current electrodes get farther away, that you're just being less influenced by this. It is interesting, and this will come into play a little bit later, that even at this distance here between the positive and the negative electrode being 60 meters, okay, and the layer thickness is only 8, you still do not have an apparent resistivity that's totally reflective of what's going on here. And the take-home message there is going to be that if you actually really want to see an object deep, you're going to have to put your electrodes at a much bigger spacing than the depth of the target that you're interested in. For anybody who's done marine EM in looking for hydrocarbons, if you've got a hydrocarbon that's 2 kilometers deep, you're going to need to have a towed streamer that's 6 or 7 kilometers long. And that all kind of comes from this. So in summary, here for a sounding solution, so we're progressively going to increase the length of the array. We start out small and then we gradually increase it, so I can kind of get all the way back. We're going to end up with the curve. This this is apparent resistivity as a function of some scale length, right? So that's not really telling us what the Earth looks like. In order to do that, we actually need to go ahead and invert the data. So the whole concept of inversion is that we're going to start off with our survey, collect the data. Here's our data. Now we're going to take those data, we're going to invert them. We're going to do this processing to actually recover something that has true depth and resistivity. So in this case here, the red line is the output from the inversion, and this is the true depth, and that's the resistivity. Turns out it's not exactly like the real model, but we were looking for something that's a little bit smoother, but this actually fits the data. There's some valuable information. So that's the process.
May I ask, is the distance between the M and an N, is that important? So between the measuring voltage distance?
Actually, not so much generally. Yeah. Because especially in the cases that I just showed you, for instance, if you had a whole variety of M and N's, the data look different. But the information content that they have about the Earth model is actually pretty similar.
If the distance gets too small, then you're not going to be able to make reliable measurements.
That's right. So there's some practical, exactly. So there's some practical issues here. If you make them too small, then you got noise that's coming on, and you have an unreliable measure. There's a concept that I want to bring up here, and that is like what happens. I talked about these currents that are kind of going through the body. So that we've got a current from here, goes through this body, and then it comes back out here. And what actually is going on here? Let's just take a little bit more of a look at that. First of all, it's steady state. So that means that the current has to be a constant. So if I look at the normal component of the current as it's crossing that boundary, it has to be constant. Okay? So the current on the left side is equal to the current on the right. But Ohm's law says that J is equal to sigma E. So that means that sigma 1 E1 is equal to sigma 2 E2. So if sigma 1 is not equal to sigma 2, so we're going through something, then that means that E1 is not equal to E2. So that means I am going to have a change in the electric field from this side to that side. So that's an important consequence. So you imagine I've got something coming through, and now the electric field changes discontinuity. So what's going on there? I've already got the answer here, but maybe you can tell me from first year physics, what is the way that you need, or what is the physical basis for having something that sort of instantaneously, as you're going across, will have a change in the electric field?
Direction of current.
No? Anybody?
Is some accumulation of charges?
That's right. So if I have a plate, remember I have like a dielectric plate or something, if I just put charges on that, so if I have a plate, a positive charge or something, then the electric field for the positive charges goes out both ways, right? So now if I'm looking at the electric field as I'm going across here, out here it's pointing this way, out here it's pointing the other way, so it's discontinuously changing. So that's what's happening here. So as I'm putting a current through there, there's actually going to be a charge buildup. And it's those charges through Coulomb's law that actually gives rise to that electric field that I measure up top, and hence my potential difference. Charges there play a huge role in electromagnetics. Here's one basis for it. So let's just take a look at that a little bit more. So let's go back and now let's put in a sphere. So we're going to have a conductive sphere in here. And so the current's going to come in through here, and then here's the A electrode, here's the B. And I think intuitively, just because of what we'd already said, what's going to happen to the current? What's going to happen to the currents in the spheres? So imagine you've got initially just a homogeneous background, and now you plunk in a big conductive sphere. What's going to happen? How are the currents going to change?
Concentrate.
Yeah. Yeah, so they're going to kind of get sucked in, right? So it's the same kind of idea as we just talked about with a conductive layer. You know, the current's going to try to take a, you know, effectively a path of least resistance, and they're going to get kind of sucked in. So you can see here they kind of jump up, and then here they kind of go down.
So you have a change in direction across the interface of the current.
Yeah, the currents will change direction at the interface, yeah. But the reason that they're doing it is because the electric field is changing. The reason the electric field is changing is because there's charges.
Okay.
So so that's the total currents. If we subtracted off just the currents from the half space, then actually what we call secondary currents look like this. So here now we've got secondary currents that are coming from. So what's happening here? Let's look first of all at the charges that are built up. So there's negative charges on the left side as you go from a resistor into a conductor. And then there's positive charges on the right where we go from a conductor to a resistor. So in order to make that continuity of currents, these are the charges that are built up. And those charges give rise to electric potentials that you can measure, and this is what they would be. You've got negative potentials here, positive potentials here. We're going to be sitting up at the surface of the Earth, and it's really that change in those potentials that are going to be, that's our signal. That's the thing that's characteristic of that sphere. So let's take a little bit more of a closer look and to see, okay, how is that DC resistivity experiment going to work? So we've got, let's suppose, a 500 ohm meter background. We got a very conductive sphere that's 1 ohm meter. Here's our charges. And now I'm going to put down my probes here to measure my potentials. And when I do that, I'm going to give, put it into my formula, and I get an apparent resistivity of 430 ohm meters. So it's not 500, but it's less, so it's something less than 500. And that's reflective of this, this conductor that's down. Depending upon where I go, I get a different number. So if I put my probes over here, M and N, I get an apparent resistivity of 502. So that's kind of interesting, isn't it? I've got a background of 500, and I've got a conductive sphere there. And when I was sort of over here, you know, this seemed intuitive to me, like, oh, okay, I've got an apparent resistivity that's less than my background. Good. But what's happening here? How is it that we could actually get an apparent resistivity that's larger than the background?
Sucking.
Pardon me?
Because the sucking of current to the ring. You have less current measured, then calculate larger apparent resistivity.
Maybe. There must be something to compensate for the other part.
If you take apart the current from the half space and from that sphere, at that location they might counteract, so that secondary current from the sphere reduces the original current.
Right. Yeah. So that's definitely one way of looking at it. The other way is just to kind of think a little bit more about what your potential measurements really are, and what the relationship is between the plus and minus signs of your voltmeter and these charges that are here. So we can take a look at how these charges, which are really the source of the measurement, are directly affecting that. But your comment is is actually also correct. If you, and it kind of depends in DC resistivity whether you like to think in terms of currents or charges. But if you look at the secondary currents here, you can see that this current is actually going this way, and over here it's closing. So it's actually adding to the primary, which is why you get an increased value. So we've got, we come along here, and depending upon where we put our potential measurements, we ended up with resistivities that are higher or lower than what the background is and reflective of that conductive volume.
It's not that the total sum of resistivity ends up with 500 ohm meter.
Sorry?
Well, if you do all these measurements, you add up take the average again of all the measured apparent resistivities, do I end up with 500?
No. You're going to end up with, well, if you looked at all of them, maybe it's best shown in this example here. Well, if I sit back here, so if I looked at the complete profile, we'd have apparent resistivity that's basically 500, and then if I did a whole bunch of measurements here, they're all going to be less than 500. So there won't be anything but with the average. The average would actually look much lower than 500. So that was sort of sounding. We sit here and then we kind of look deeper. The other is profiling. And in profiling, you're basically taking an array and then you're moving it along. So here I could have, let's say, an AB electrode and an N electrode. And so that would be my survey. And then I just sort of move that along. And if I did that, I'm going to do it again over the same example. The apparent resistivity that I get is basically going to be 500 ohm meters all the way along, because all the only thing I'm seeing is just the effects of what's happening very near to the surface, and that's just going to be up here. If I extend the system and just make it bigger, okay, have something that looks like this, then as I go along here, then I'm going to get a profiling curve that looks like this. So over top of the body, I'm actually going to have a apparent resistivity that's significantly lower than 500. And again, I'm going to be seeing that there's these overshoots on the other side. So that's sort of the idea of profiling. And that's sort of two ways that you can kind of think about acquiring data. One is to make things bigger, and the other is to go in and translate things along. There's a number of words that you'll see. Yeah.
So, but if we have the layered Earth, we also have at each layer boundary, we have this charge being set up.
Yeah.
With all the layer boundaries. Yeah.
That is true.
Because you show it for the sphere, but
that's
the
right.
layers,
No, every time you've got a current that's crossing a boundary, there's going to be a charge buildup.
that's a way to look at the field you measure. Yeah.
That's right. And often when they talk about currents, they'll talk about, currents are refracted. Right? So, okay, so what's going on there? Well, they're refracted because the electric direction of the electric field is changing. Okay, so why is that? Well, that's because there's charges.
But the charges are constant if you do a DC, because you don't change the current, so they start up from 0 to a particular charge level, and then it stays like that.
That's right. And that time to actually get that going is, for all intents and purposes, instantaneous to develop that DC charge. That'll happen very quickly.
Okay.
So there's some basic setups here. These are words that you'll come up. There's Wenner and Chambertin, we've already talked about. Gradient, I've also talked about. Often in gradient array, they'll put currents out here, and then you just measure the potential difference as you're going along here, so you don't have so many sources. Then you'll have things like a dipole array. So here you've got just a current, and now you've got your potential. So they can just sort of move along in some transit. The things that you'll often, especially in mineral exploration, is like a pole dipole. And in that case, one of the current electrodes is just dragged way up to heck and gone. You always need to have four electrodes in the system, but if you run one out, 5 kilometers, which they sometimes do, then that one really doesn't play much of a role. So effectively, you just got a pole, or you can have a pole. So those are words that you'll see, the different ways of acquiring data, and a lot of it has to do with kind of depth of investigation and signal too. So if you have DC data, then you want to be able to somehow plot it and to look at it. So it's convenient to be able to plot data on a map of some sort. So here's how it's often plotted. You'll hear the term pseudo-section that is used. So we've got currents and potentials, and we're going to calculate the apparent resistivity through that formula. And then we're going to plot it. And one way of doing it is to construct, let's say, a 45-degree angle from each place here, and then we're going to plot it here. If we move this guy farther away, then that angle is going to plot farther down. And if we move it farther away, plot it. Okay, so that's basically how it goes. And if you're going to so what we're doing here, this is how data would be acquired. So you can see that for each current electrode, one guy on the left, so we fix him, and then this guy moves progressively out. As he does, then we get sort of a line of data, and then this current moves over, and then you say it again, So that would be like a dipole experiment. So we're gradually going out, collecting the data. And then here's your final section. So here's a way of plotting up your data, and if you simply acquire data on a line format, and in this case, blue is resistive, red is conductive. You can see, okay, there's some stuff here that's conductive. This picture does not tell you anything particularly about what the geology is really like. It's a way of plotting the data, and that's basically it. But anyway, that's how it is, and that's what a pseudo-section is. So as I said, that doesn't tell you information about the Earth. The pseudo-section was just a pseudo depth and horizontal distance. Some examples of this. If here's a case where you have a buried conductor. So this is sitting inside a homogeneous medium. If you go over and do that DC resistivity experiment, here's your pseudo-section. It kind of looks like this. So you can see, well, there's something really interesting happening here. And if you knew a little bit more about how these things generally look, you might have made an inference that there's something interesting there and spotted a drill hole. And in that case,
excuse me, why is it not looking symmetrical?
It's a little bit just way in which the data were collected, and yeah, so it wasn't quite symmetrical.
Because of the data acquisition set up.
Yeah, otherwise, if you had the array completely uniform and everything symmetric and didn't add any noise to the data, then that's this case is actually interesting, because if you take a little bit of few conductive features up here, put them in a surface here, and you do the same experiment, now you get something that looks like this. So on these are your data now. So that looks very different from what you had, and this is completely unintelligible from the point of view of the geology. And here's another case. It's two buried conductors in here in a variable upper region, and the pseudo-section looks like this. So it's got this red region here, tempting whenever you see something that's like, oh, let's drill that, see what happens. But in fact, if you drill this guy here, you'd actually be drilling right through region here, so you'd have targets on both sides, but you'd have missed everything. So that's not a good example. Anyway, so that's the point about that. That's the experiment, and this is the data, the student section. So clearly you need to do something more, so we need to invert the data. And here's the sort of cartoon sketch about how that works. We're not going to do this tomorrow. If people want, we could do a bit of a tutorial on this, but we've got too much other stuff to do today to talk about the inversion. So I'm simply going to say that the process for the inversion, both of this 2D and any of the 3D stuff that we do, is basically the following: that we're going to take a mathematical model of the Earth, divide it up into a whole bunch of uniform prisms or cells, and adjust the values of those till we fit the data, and also are consistent with some kind of geologic information about simplicity or other more explicit information that we have. Okay. So if we come back to this very prism, for instance, here was our pseudo-section, and then if we take those as data, invert them, then we get a recovered resistivity that looks like this. So this is actually kind of good, right? We're looking for conductive prism. We've got it centered in right location. It's smooth on the boundaries, but it's smooth. That's because of the inversion process, where we were looking for kind of smooth bodies that would reproduce the data, and we end up with something like that. So that's a great result. You drill that, good to go. If we look at this example, which was really kind of mucked up because of all of these guys here, you see that we've done the inversion cell has not only recovered the object that we're looking for, but it's actually done a pretty reasonable job of finding these near surface conductors. So they may have, in fact, I mean, they might just be geologic noise, but yeah, maybe they're kind of useful. But the bottom line is there is enough information in these data. Okay. There's enough information in these data to recover that. And if we look at this other model with two prisms, then the inverted model looks like this, and now there's simply no question about the fact that you've got two and spotting some drill holes.
Is it the surface geometry, so the valley, is that through the white part, is that the valley?
Oh yeah, so there was topography in here, that's not.
Is that the main cause of why you don't get it?
It's a contributor, yeah. Yeah, topography turns out to be really important in DC resistivity experiments because you get all kinds of charges that are built up on surfaces. Okay, so that was, these are just kind of like, we're just sort of stepping through the basics, but these basics are actually turn out to be kind of important. So if we're up to 2D, we're fine, but the world is 3D. That makes things more complicated. Here's some 3D scenarios, and first of all, maybe you've got a target. So what's the size? What's the shape? What's the depth? What's that background resistivity? Complicated. And then there's some practical questions like, okay, where do I put the currents? You can put the currents all kinds of places. Should I use a 2D acquisition or a 3D acquisition? And then if I put the currents in, where do I make the measurements? And which measurements do I want? Which electric fields? What about the effects of topography? So there's a lot of survey design questions, and anybody who does anything in geophysics is always concerned about survey design because there's just so many options out there. So how do we approach this? Well, the crucial element here is sensitivity. So if I was just to ask anybody to provide a definition within the context of what we're talking about for sensitivity survey design, what would people answer? Go ahead.
If I change a little bit my geometry of my target, would I see that in the measurements?
Perfect. Yeah, so you're trying to see if you're actually sensitive to the target. So you change something you know, the geometry, the value, whatever. Do you actually see that? So that's actually what we're just going to spend a minute about and talk about. So here you've got your system set up, and the real question is, well, here's your target, and you know, am I somehow sensitive to this target? And we're going to quantify it by exactly what you just said. We're going to, if P is our parameters for our model, we change them a little bit, and then we're going to get a change in the data, and that ratio is just going to be effectively our sensitivity. The thing that's really helpful, I think, in this regard, when you think about sensitivities, is that it's good to divide it into two parts. And the first part is that you need somehow to excite the target. Okay, so that's the first part. The second is, okay, now I've excited the target. Now I need to measure something, in which case you need to kind of make sure you've got the right component and that you're somehow close enough. But it is actually very, I think, important from the point of view of sensitivity to divide it up into these points, because then it just helps clarify things. So let's talk about that. So first of all, we're going to think about exciting the target. So we had current electrodes that look like this. Secondary fields, but we produce these charges here, right? So that's good. So we know that this particular system here was actually useful for exciting that target. And for measurements, once we have understood that, okay, we've got these negative and positive charges, then we can, since all we're doing is measuring with a voltmeter, we've got a pretty good idea about where we might get the largest signal. Clearly, if we had a voltage probe down here, we do the best. But if we're sitting up here, you can tell that, okay, we're still going to be pretty sensitive. So the sensitivity, dividing it up into two parts, and we'll kind of do that throughout the rest of the day too. We're first of all going to concentrate on exciting the target, and then once we've done that, then we can figure out what we should measure. The other thing that's really important is coupling. And that's going to be the sort of orientation between your target and the field. And so in this case, we've got a target that looks like this, so it's sort of going into and out of the board. And we can tell that you can sort of see how the currents are getting deflected in when they look like this. When the target is rotated 90 degrees, it's on the side like this. So you can see how the currents are being distorted. So depending upon the orientation of the target that you're looking for, if it's got geometry and those background fields, you're going to get different distortions, and it's going to react differently. The last thing is your target. Like, does it matter conductive or resistive, and which is excited most? If we have a conductive target here, so our currents are coming through like this, and we look to see what our charges are on the outside boundary, then we get negative charges here, positive here, and a certain value. A resistive target, you can see how the currents are sort of going around here. And so they're being quite distorted. If you look at the total charges, they're actually quite large here compared to back here. And notice also there's a change in sign. Right, so here, the currents that are coming in through there's a negative charge and a positive charge here. If I change the resistive instead of conductive, now I've got a positive charge on this side and a negative charge on this side, and the magnitude is larger. So there's a lot of things here that are really different, even if you have the same, plate, but depending upon whether it's more conductive in the background or less, that's certainly going to really affect it. So in in summary, then, for the sensitivity, we somehow need to drive currents into that body. We need to be worried about coupling. Coupling is going to be really important throughout the whole day, especially as we're starting to talk about inductive sources. And then we need to measure, so we want to be in proximity to the object and use proper electrode orientation. And the other is that the background resistivity is going to be important. So those are elements that you need to at least address and think about conceptually as you're going through things. So then we have the question of like survey design. So again, we're in that same kind of quandary. If the Earth is 1D, okay, then we kind of know what to do. We just do a sounding. We're good to go. If it's 2D, okay, we can do a sounding and a profiling. That's fine. If it's a 3D structure, however, then we need to have somehow 3D coverage. So people from seismic are kind of familiar with that. I mean, and nothing has changed here. You just need to illuminate this object from different orientations. So that's first of all the objective, and you have to come to grips with that. You're like, okay, what is it that I'm trying to look for? What are these scenarios? The next is, okay, well, what's that background resistivity? What's my host looking like? And then there's questions of noise, fences, power lines, different kinds of noises than you're used to thinking about for seismic. There's no black box solution to anything that you can say about survey design, just the same as in any of the seismic techniques, right? You really have to basically go through a particular scenario and by something like this. So you've got some kind of a background, you've got some targets in there that you're hoping to find, and then you're trying to address, okay, can I find it? Is my survey going to be good enough so that I could see that? And the steps are really as follows. You first of all have to define geology, physical properties to that, hypothesize a survey, and then acquire the data both with and without perhaps the target of interest. And in this case here, without the target, you can maybe get this dashed line. With the target, you got something that's different. So you can look at that difference and then try to make some assessment as to whether that's big enough that you're going to, it's going to be useful. And I think maybe the only thing that's, or at least one of the things that's important here is this question, big enough. And there's two elements that play a role. One is that basically the absolute value of this has to be greater than some floor. There's always some background noise that is existing. Is relative value of this and the primary is at least a certain percentage. What we'll see in most of the experiments, especially since you've got many orders of magnitude in dynamic range of the data, that a reasonable description of noise is actually a percentage level, and then maybe something like a floor value. So those are the two things that really kind of crop on. So those are kind of the basics. We're gonna, most of those things, even though they may seem a bit trivial or seen them before, we're gonna encounter them in various guises as we go through all of the rest of the stuff. But what I'd like to do now is just turn to a case history. So this is a mineral prospect in Australia. So sure you can see that. That's a map of Australia. This is the region up here into the north. And I'm going to kind of step through this in a 7-step process. As I said, we're going to have a setup, properties, survey, kind of go through that. So the goal here is to find this mineral prospect. First of all, the setup. Okay, what's the problem? We've got an area that we're trying to find a mineralization. There's a geology that's kind of characterized by this cross-section here. There's a number of different types of rocks, each of them kind of color-coded. There's some volcanics, there's some siltstones and clays that have got some mineralization in it, and then there's a few other things. But the basic question at this point is, okay, can we find a conductive unit in a potential target for mineralization? Can that be identified with? Look at that. Identify the various rock units that are there and kind of figure out, okay, what's the physical properties, because it's the same with all geophysical experiments. The target body that you're looking for has to have a physical property that differentiates it from others. So we've got these different units here. It doesn't really matter what they are. The important thing is from a conductivity perspective that there's a few things here that have moderate conductivity. It's those are basically siltstones. The thing that we're looking for is something called, well, it's called Mount Nova Horizon. It has a high conductivity, so that's good. It differs from these guys. But it's not the biggest kid on the block. There's something else called a breakaway shale that has a very high conductivity. Okay, so from there's a number of different rocks. The thing that we're looking for has got a high conductivity, but maybe not the highest, and it differentiates itself from these other guys. So we're going to do a DC survey. Here's our area. It's pretty flat. And also the geology is pretty much north-south. So they've kind of known that before. So what they're doing is doing 10 lines of data. So just as I was showing you earlier, so 10 lines of data. And they're doing a pole dipole. So remember, it's just a single current, and you're measuring the electric potentials up here. So they put up a whole bunch of electrodes surface, and then they gradually come along and they do a pole dipole experiment. And there's 10 pictures here because there's 10 lines of data. So what are these telling us? Well, the red is indicating things that have a high apparent conductivity. Blue is really low. And you see that, okay, these 10 lines, there's some differences. Looks like it's redder to this side. There's certainly some red things that are coming in here. But those are pictures of data. They don't really tell you what's happening geologically. So remember, from the point of view of survey design, you wanted to excite the target. So if I've always got the current like on one side, I'm exciting things in a particular way. But it might actually be better to change where the currents are. So rather than do this, let's just flip things around. So let's put this other current on this side. So now we've got kind of like a dipole pole. Okay. And now we've got 10 more pseudosections. These are different, right? It's redder over here. So I'm exciting Earth in a couple of different ways. I now have 20 pictures. There's only one Earth model there. So somehow what I'd like to do is to combine these guys and the previous ones into a three-dimensional model by carrying out conversion. So that's what I'm going to do. So the procedure is just as I outlined in 2D, but now we'll take a 3D cube, if you like, divide it up into a whole bunch of prisms, And then we use the inversion algorithm to find out something that fits the data is also some degree smooth. I'd like to preface this. I'm actually particularly, well, I'm actually quite proud of this result. It was something that was done a long time ago. We did it in the mid-1990s, but it was the first 3D inversion for DC resistivity data that had been done for a mineral exploration project. So it's kind of, I mean, it's, so in a way it's an old example, but it's actually kind of nice because it was one of the first ones. Okay, where's our, look here. Huh, where do you go? Oh, here we go. Okay, so what we're seeing here, I'm just going to flip it through. So here's our 3D cube of the inversion. And what sort of flipping through, cutting it north-south, and we're on plan view, and then we're going to rotate it around. And what's happening now is that the isosurface values are continually changing, and we end up with the highest region of conductivity. So let me just do that again. Okay, so here's the inversion. We're slicing through it now in, from north to south. You see that there's some, red stuff here, that those are highly conductive, and these have very low conductivity. And that red conductor continues on that side. There's something interesting coming in here. It'll play a role a little bit later, but you notice there's another conductor that's coming in over here. And now we come back. So now we're kind of cutting down on plan view, and it's very traveling north-south. There is something else up on the side. Predominantly, the big hit on the block is that guy. And now as we start to rotate this, then we have plotted sort of isosurface, but the threshold value continues to change. And we're going to be left with the highest conductivity unit that's there. So that's what it looks like. So that is your 3D geologic model that is coming out of the DC resistivity and plotted in color scale, kind of looks like this. So that's what we get out. And then the next step is, well, what does all that mean? So first of all, it's actually quite great. I mean, we've taken DC resistivity, we've got now a three-dimensional Earth model, which I must admit the geologists were really quite enthralled with. And now the question is, okay, what is this? Well, it turns out this guy here, this big conductor, is a black shale unit. They knew that that was around, and it was pretty easily distinguished. And it runs north to south. It's unfortunately not mineralized. So even though it's the biggest geologic unit that's there, it's not of economic interest. There is another unit I pointed out a little bit. It's sort of moderately high conducting. And remember I said when we did the physical property table that the thing that we're looking for is a high conductor, but not the highest. And the manifestation of that is kind of here. So So that's kind of where we are, very much a geophysical success. It's not the end of the story by any stretch of the imagination, because this deposit is characterized not only by conductivity, but even more so by electrical chargeability. So in addition to the DC, there's also going to be an IP experiment. We're going to do that right at the end of the day. So I'm actually going to close out the day with this particular survey, but show you what actually happens when we do the IP. I think I'm going to, I do have a case history for dams, which, I mean, you got lots of dikes here. I'm not sure where you are with respect to integrity of dikes or how all of that matters. But there's a lot of places in the world where you get dams that are kind of sitting up like this, and maybe they're have a little bit more of a structure in that looks like this, and they could be quite large or they could be smaller. Here's maybe a cartoon of something. This particular case history actually looks at the use of self-potentials and DC resistivity across this dam to see if you could determine where the leakage might be here. So it's really, it's kind of like DC resistivity. It's something called self-potential. And if you've got a fluid that is moving through a porous medium, then you can get what's called streaming potentials. Basically, it's charge buildup. So everything kind of comes back to charges. And these charges are built up. Yeah. So these charges are built up as, like, you've got a little bit of a conduit that's coming through here. Then the charges can get positive charges at one end, negative charges at the other, and you can measure the potentials as you go around here. And those potentials would be then reflective of these charges, and you can invert to try to find information out about how the electrical currents are flowing through here, and ultimately try to get your way all the way back to understanding if there might be a leakage pattern there. So that's what this is about. We're not going to go through that, but we can if people are interested. What I want to do is just kind of conclude with one thing that I'd mentioned earlier, and that was the looking at the effects of the background resistivity. So here's where we have this homogeneous medium here, 500 ohm meters, and a big conductor. When we put a currents in, they got kind of sucked in here and had apparent resistivity of 430 ohm meters. The question now is, like, suppose that I put in a background region in here. Let's suppose I put in a little layer of high resistivity. Okay, so let's just take a little layer of high resistivity. What's going to happen?
Above the conductor.
Pardon me?
Above the conductor.
Above the conductor, yes.
I would do the.
No, but what's
yeah, no, I know. No currents would flow.
Pardon me?
The amount of current that would flow through the high resistive layer is very limited, so there would hardly be any current in the lower part.
Right? Everybody?
I think it would help.
You what?
I think it would be helpful in detecting the conductor deeper down.
Okay.
You will find conducted layer, but not below it. Because you don't have signal anymore.
Any others? Okay, good. Sounds like you guys have got pretty good handle on things. Yeah, so if I put a resistive layer in here, then all my currents, I'm not going to be able to penetrate that resistive layer with a DC survey. So all of the currents are going to be sort of funneled into the region above here. And yeah, your apparent resistivity is actually going to be large because you're effectively just seeing this resistor down. So that means that even a very thin layer of something that's very resistive from the point of view of DC resistivity can be a real challenge here. And just to accentuate that you really are only seeing that resistive layer, if you take and do the modeling without the sphere, just have that resistive layer, and you get essentially the same apparent resistivity. So the DC resistivity experiment was fine, but if you have a host that is not very favorable, that can completely distort. And then what happens if you have a conductive layer? Perfect. Yeah, so that's exactly what happens. So if I have a conductive layer in here, now all the currents just kind of get sucked into the conductor. You go along this conductive layer, and it goes. So there's really nothing that's going on here. And again, if I do it with this, with the sphere and without, I get essentially the same answer. So the only thing I'm seeing then is that background. So it's, and really you already alluded to it, okay, we're kind of hooped here with the DC resistivity, so now we need to go ahead and do something with electromagnetics. Right? Yeah, we're going to quit. That was it.
Yeah?
Yeah. So let's have a coffee or questions?
Yeah. The charge build-up might take some time. So are you going to use that also then later in the energy measurements? The time it takes to build up the charge, and then you take away the DC potential difference, and then you wait until how quick the energy flows again.
That's really the IP experiment.
Oh, that's right.
Yeah. Yeah, so we'll come back to that.
Another question is actually conductivity anyway related to permeability? Because the electrons need to be able to travel through the fluid.
Yes.
So.
Yeah, so there's, that's, having important connections and really actually on, and especially with the IP effect, to look at fluid flow and electrical and the IP, because they're both kind of surface area topology things, and connectivity, looking at how the fluids are actually.
Okay, so IP is then an experiment where you can sort of determine in a way permeability. Or is that going too far?
That's a bit too far. It's still going to need something about permeability to really get what the flow velocity is.
So for the IP, also it gives an indication of the pore threads.
Yes, that's true.
So,
yeah, so you can get a polarization, like a memory polarization there that will. That's related then to pore throws, how quickly the charges will build up and how quickly it will.
Thanks.
Yes, I can see that. Yeah. Yes, that's great. And so for mostly monitoring applications, the casing
It's a survey somewhere and in the data. That's better.
Well, I'm interested in
Yeah, looking at modeling. Yes, so you just kind of zoom data. So you have radial. Yeah, so all of that is kind of the 3D so much is development. If you're interested, like, I can show you.
Yeah, there was a reference to one of your
Right, yeah. So that was the 2D stuff. Yeah.
But I didn't spend much time on it, and it seemed like it needed some setup to get it going.
Yes, it does need a bit of setup.
Yes. That's where I stopped.
Yeah, that's fair. That's very fair. Yeah, but I'll share some of the research. Ways of getting these up. Some of those research are very much. We have examples.